Thank you very much for joining. Welcome back to 3DGB. We had a break last week due to many other events. So let us congratulate on the CVPL submissions. I know many of you worked on those. Also congratulate on the USA presidential election, the most numbers of voter counts in the 120 years of history, in the last 120 years. So today we have exciting program again. David Fouhey from Michigan giving a talk, joined by two panelists, Vangelis from UMass Amherst and Derek Hoyam from UIUC. So David Fouhey got a PhD degree from Carnegie Mellon University under the supervision of Abhinav Gupta and Marshall Ebert. Then spent 2 years at Berkeley with Alyosha Efros and Jitendra Malik. He is currently assistant professor at the University of Michigan at CSE, also affiliate professor at Robotics Institute. And David will give a talk on 3D scene representation today. So David, please take it away.
Let's see. All right. And can you see my screen?
Oh, yes, it's working.
Okay, great, wonderful. Thank you so much. And thank you so much for having me. Thank you to all of you who are joining. 2 days after the CVPR deadline, I'm going to try to make this entertaining and have lots of pictures and less math. It's a great pleasure to be here, and thank you to all the organizers of this series. I think this is a fantastic idea. So this is
I forgot to mention, as usual, for anyone to ask a question to the panelists, please use the YouTube chat box below to type any question anytime to panelists or David. Sorry, David.
Thanks. Yeah. So this is joint work with two of my students, Lin Yi Jin, who is applying to grad school this year. He's a master's student in robotics, and then Sheng Yi Jian, who's a PhD student with me. And the work's been generously sponsored by Toyota Research Institute. Okay, so I'd like to begin my talks with a picture. So here we have the Fairmont Mayakoba. You may not have been there. You might be thinking about what can I do after submitting my CVPR papers and dealing with all the stress. So I'd like to ask people to actually sort of look at the picture and imagine what you can do in this scene, because I think this is a useful exercise. And so take maybe 15 seconds and look at the scene. So there are lots of different things you can do, and so we can go through a few of them. So you might, for example, you might say, oh, I want to go outside and look at the sunshine. Here in Michigan, it just recently snowed. So this nice warmness outside is a very good thing. You can imagine you can walk out there. You can walk out onto the porch. You might say, oh, I want to sit and I want to read something other than my CVPR paper. And you might walk around the bed onto the floor behind this bed. You might even just say, okay, I just want to take a nap. And hopefully this talk will not cause you to take a nap. And you might hope that you don't dream about seeing Microsoft CMT at least for a little while. And so you're able to understand this scene and reconstruct it in your mind and understand what you can do. And you can understand the scene sort of volumetrically. And you know that the floor continues behind the bed. You know that the chair is on top of the floor. You have this great understanding. And the goal of my research is really to mimic this ability in humans. And I've been giving talks where I start off with a single picture for a while. And so I ask people to think about what they can do. And today I'm going to be talking primarily about work which has a slightly different twist, which is, let's say, okay, the Fairmont Mayakoba it's a classy hotel. So when you're looking at the pictures online, you don't just get one picture, you get multiple. So what happens if you have two images? And so here we have two images from a place. That's the only information we have. And yet, despite this, you have a very good idea of what's going on. And so you can say, hey, look at the scene. I can imagine there's this bedroom on the left. There's the living room on the right, and this is a nice hotel room. And so you can ask the question, how many beds or chairs are there in this hotel room? And you can say, okay, well, you got the bed in the bedroom, and you can see the same bed in the living room. You can sort of count the chairs in the bedroom, count the chairs in the living room, and it's pretty easy to answer this question. And the reason why you're able to do this is you're able to solve this because you can say, hey, that bed in the bedroom is the same bed that I see in the living room. And so I can, in some sense, I can merge the two. And so hold on, I'm just going to pull up the chat. All right, I can't pull up the chat. Okay. So what I can do, so Yasu, if there's stuff in the chat I should pay attention to, let me know. So feel free to interrupt at any time. But so you can recognize that the bed is the same, but this chair, for example, it's actually different. And so you're able to build this representation from just like 2 images. And the thing is, to start out, you don't actually know where the cameras are. And so you have this amazing ability, and you use this when you look for hotel rooms. You use this to look at when you look for apartments. You also use this when a friend shows you a picture of an event that you didn't go to. And there's a photo from the kitchen, people are sitting around talking. There's a photo from the living room. You have this amazing ability to understand the 3D structure from a small number of images without a priori knowing where the cameras are and without having very much information. And you're able to do it even if there's not a lot of overlap, and even if, for example, this chair appears in only one of the images, but yet you produce a single understanding. And so the particular challenge I'm going to talk today about is given 2 images with an unknown relationship, we want a single coherent volumetric reconstruction. And by this, I mean that we want to produce an output like this. So here we have 2 images. They're actually taken from opposite sides of the room. And we'd like to produce an output like what you see in the middle. And originally this paper, I wanted to call it Craigslist voxels, which captures, I think, the essence of it. But my students didn't let me. So it has another name, which you'll see later on. But this sort of idea of you take these photos from different angles where you don't know the relationship. This is sort of like the essence, and you want to produce a volumetric understanding. And the key is it has to be a single one. So what are the challenges? Well, the first thing is, in order to understand it, like for example, you look at like this TV. This TV, there's only like one of these TVs. And you have to say, okay, this TV on the left image is the same thing as the TV on the right image. And they have to go together. And so you can do this. But at the same time, for example, if you look at this chair, well, the chair is similar, but it's actually not the same chair. If you look at behind the chair, you can see that they're not the same. And in fact, if the chairs were the same, then you would, then the pictures would be taken from different rooms. And so this is actually a very interesting challenge because you have this, you have to reason jointly across these images, and sometimes stuff might match nicely and some stuff might not. So how can we actually sort of solve this? This is, once you start adding 2 images, there's lots and lots of related work. And so I'm going to try to skim over the general trends. And I apologize that this problem, I think, touches on so many parts of 3D computer vision that's really difficult to cover it all. But sort of in broad picture strokes, you can imagine that there are very geometric ways of solving this. And this is basically wide baseline stereo in some sense, in the sense that you have these 2 unknown cameras and you want to find out 3D information. And you might say, okay, fine, I can find these points, I can find these correspondences, and by finding the correspondences, I can solve for the essential matrix or the fundamental matrix and extract information about the cameras. And so there's been a lot of work on this using classic descriptors, learned descriptors, end-to-end approaches. There's been a lot of great work in this area. Now, the reason why this is sort of in some sense insufficient to solve it is that if you look at where's the overlap between these images, the overlap covers some fraction of it, but a lot of the scene is actually only seen in one camera. And so in some sense, we have to be able to reconstruct that. We have to be able to understand it. And so what you can think about to solve this problem, we need some combination of like wide baseline stereo plus some sort of single view 3D. Now, you could imagine you could solve this. Okay, fine. I just have 2 images. I can solve this very easily with single image 3D. And there's been lots and lots of work starting from about 15 years ago with Derek Hoyam and Ashutosh Saksena's work with reconstructing sort of depth maps and geometric context. And there's been tremendous progress for the past 15 years. And there are now systems that can do things like produce sort of like, for example, the voxels of this scene. But the difficulty is we get estimates from RGB. So if we're working with a single RGB camera, then we only have an estimate of the 3D shape of the scene. And we need a single coherent answer across both images. So when the TV appears in one image and the TV appears in another image, we might not estimate it at the same location. And so we have these 2 potentially inconsistent reconstructions, and somehow we have to fuse them together. And so you can see that single image is part of this problem, but it's not the full problem. And you can't just sort of stick stuff together because some stuff appears in both images and you want to leverage that information. And finally, you also don't know what the camera, how the cameras are related to each other. So there's been a lot of work in sort of this work naturally touches on a lot of multi-view plus deep learning approaches. And this has been a topic of a lot of interest in the community. And I think this is exciting. There are different, people are exploring different parts of the space, but I think what separates this sort of work is that we have two images and we have an unknown relationship and we want a reconstruction. And so this sort of problem of both doing reconstruction plus wide baseline stereo hasn't been really as explored. And most systems either have lots and lots of images, they know what the cameras are, and or they don't produce a reconstruction. And I think multi-view plus 3D is an area I'm really excited about. And I'm curious to see which problems people start working on, which problems take off. And I guess one of the things I'd advocate is that this problem of just taking two images and trying to reconstruct the scene is very interesting. And you should definitely work on it. So, okay, so let's get back to this particular challenge. We have two images, we don't know their relationship, and we want a single volumetric reconstruction, and you want a coherent reconstruction. So obviously some fraction of this, as I said, is single image 3D. So we have sort of single image, we have to be able to take an image and produce some form of 3D from that image. And we'll really need a mechanism. And now preemptively, before I get to this talk, part of the talk, I'm going to be showing you some work from about 2 years ago, which sort of we're building upon, and a sort of representation. And preemptively, I know that voxels are bad, and they're better representations. Now, I can't go back in time and invent implicit functions before they're invented. And I also know that SunCG is a data set which is sort of not used anymore. And there are a lot of better data sets, but this was the paper that we submitted 2 years ago. So I'm going to talk about a method for reconstructing voxels from a single image that is applied to scenes. And it's a sort of a representation as well, because this representation is what we use to solve this problem of having two views, and which I'm very excited about because I see lots of applications of it. And the specific representation is this idea of a factored representation of the scene. And to illustrate it, we have this input RGB image, and we have this factored output of the representation. And what do I mean by factored? Well, the idea is that we have this input RGB image, and we want to represent the scene that it captures. And there's a question of how do you do that? You could use voxels, a depth map. But what we want to do, and what we proposed in this paper in 2018, was this idea of factoring things. So you can say, here's a chair, and you have the chair over here. And I might know a lot about the shape just looking at the chair, but I might not know where precisely it is. I might not know its precise rotation. I might think it's a little bigger than it actually is. But the idea is you want to represent these components independently. So for every single object, we're going to represent the object as a set of voxels. So here it's 32 by 32. And then some sort of transformation that puts it into the scene, starting from the origin of the camera. So we have the voxels and we have the scale, the rotation, and the translation. So you can think of it as I decompose a scene in the image into objects, and I plop them into the scene in 3D. And this idea is that you sort of decompose a scene into these components. And of course, voxels, we should just forget voxels, just use implicit functions. This will produce better results. But the important thing is that this is kind of independent of the 3D representation you choose. And so the idea of sort of factoring the scene is, I think, independent and can be repurposed a lot. Okay. So of course, if you have these sorts of things, you're going to have immense amounts of supervision, which is one of the limitations. But you can imagine that you're able to take, you have an image and you have a collection of bounding boxes. This might come from a detection system. It might be proposals. And for every single object, you're going to try to produce the voxels, the scale, the translation, and the rotation. And of course, you need to have supervision for these. But if you have the supervision, and you can get this from, for example, synthetic data sets like SunCG or any of the successors to it, well, you can solve this in a detection framework. So you take a backbone, you do ROI pooling, or ROI align. And then after ROI pooling, what you can do is you can pass it through some layers, and then you're going to predict a bunch of these properties. So you can take this box, you take the ROI in the feature map, and you predict the voxels. And so you can think of this as it's like a detection system plus voxels stuck on top of it. And you can predict also the scale, the translation, rotation as well. And so essentially what the system does is it detects the objects and reconstructs them at the same time. So this is the approach that we were taking in 2018. One of the tricky things that we ended up finding out, which was interesting, is that in scenes and the objects we tend to deal with, rotation ends up being a pain. And often it's ambiguous what the rotation is. So what we ended up having to do is, because these results tend to be highly multimodal, in the sense a table could be at either 0 degrees or 180, and there's an annoying ambiguity in the silhouette of chairs, for example, that causes them to be off by with sort of a similar thing occurs. You end up having to use classification, and this tends to produce better results compared to regression. And it also produces a set of hypotheses as opposed to a single best guess. So I'm going to show you the results of the system in action. This is SunCG, rendered with a physically based rendering system. And so here's the ground truth. And so we're not going to reconstruct all the objects. We have sort of 6 that we care about, because otherwise we end up reconstructing, most of the time we're reconstructing like vacuum cleaners and little tiny flower vases and these little individual fruits on the table. And so here is the ground truth from the camera view and another view. And here's a prediction from our system and from the same camera view and sort of tilted above. And keep in mind that this is coming from a single RGB image. So you can see that it gets a general structure pretty well. There are, of course, details that aren't correct. It's not perfect yet by any stretch of the imagination. But let's zoom in on one. And so here we have a bedroom. You have the bed, you have the TV stand, you have the TV, and it does a pretty reasonable job at capturing the general structure of the scene. And so this is sort of, we're able to do a reasonable job. And this is quite exciting because this is all from a single RGB image. And for many of the people who are starting out in computer vision these days, you've seen lots of cool results. And so results like this don't quite seem as exciting. But for someone who started off way before deep learning, or a little before deep learning, these results are these were like the sorts of dreams that we were hoping for when I started. And so getting results like this from a single RGB image is quite nice. So we train this on synthetic data. Now, the natural question you might have is, does it work on real data? The answer is, it works okay enough that we have qualitative results that we can show in the paper and are not really embarrassed. So here we have NYU V2. And so here we have the prediction. And so here's a prediction, and you can see it gets the tables and chairs in the back in the first row, and you get the TV. We can sort of render it from another view. Now, of course, this is not exactly a reconstruction you're going to sort of want to send your robot in using, but it's exciting that you're able to get this from a single RGB image and trained on synthetic data. So we're able to reconstruct these sorts of factored representations, and you can sort of produce them from a single RGB image. And
hey,
so,
David, can I ask you a question?
Yeah.
So can you say something about the gray voxels in the background? Like, how did you get those, and what does that represent?
Yeah. So sorry for not mentioning this. We also produced a layout. So there's been a lot of work on reconstructing boxes of scenes, and so these were also we also predicted at the same time, mainly to so that they weren't objects sort of floating in thin air. We produced this sort of floors and walls type stuff. So this is like an enclosing surface that we also predicted. Yeah. Does that answer your question?
Yep. Actually, is it like a free-form layout prediction, or is there some structure to it?
It's a totally free-form thing. So we just predict the disparity. So it's it in principle captures basically, it's just like it's per pixel, and then we sort of push it back and make a mesh out of it.
And it's only layout and not foreground objects, right?
Yeah. So it intends. I don't remember the specific criteria for what the pixel counts for, but it's intended not to be foreground objects. It's supposed to be sort of this enclosing parts of the scene.
Right. Thanks.
Yeah.
And the quick question from me: do you also predict the RGB color for each voxel, like texture?
No, unfortunately, no. So this is the voxel prediction system we're using. It's certainly going to have it's going to have issues with this. I think what's exciting is that there have been all sorts of there are people working on different problems with different types of data. And I think revisiting some of these problems with the much better sort of per object prediction systems would be really exciting, because you could imagine you could reconstruct them with the texture or color. But here we don't. And they're also low resolution as well, which is a shame.
Yeah, that's totally fine. That's great progress, I think. Yeah.
So once we have these predictions, one thing you can do is you can sort of place them in scenes. And so here we have the rendering of we have these sort of the rendering of our system as output. And rather than show you numbers, since I figured that I think the more important lesson from this result, rather than the numbers, and I promise there are numbers later, don't worry, is that you get this output which is sort of factored. And we thought this was important when we started. We thought that the representation should be factored. You should have individual objects. The object should have a location and space and an orientation. And we didn't quite know why it was important. But what we found is that we actually could, once you have this representation, you should be able to do things with it. And so, for example, one thing you can do is you produce this output. And they're okay, there are only 2 chairs. We didn't get all 6 of the chairs. But we got this from a single image, and this was trained on synthetic data. But what you can do is you can say, okay, I don't like this table. Let's get rid of the table. Delete the table, totally fine. And this is just a manipulation of the representation you get. You can render it from another view. And so you look at it from above. And if you say, hey, I want to move the chair out, you don't actually have to change the voxels. You just have to change where the voxels are located. And we thought this was important. We argued in the paper. We said, oh, this is useful for downstream tasks. We didn't really have one in mind. But what ends up happening is that this fact that these things are sort of factored, what it does is it accounts for the uncertainty in an interesting way, where rather than having this sort of smear of voxels, sort of the convolution of the shape of those chair with where it could be, you get a pretty sharp guess of the chair shape. Now, of course, the network might be secretly just doing nearest neighbors, but you get some guess of it. And you have an idea of the location, and the 2 things are separated out. So it's very easy to manipulate them independently. And this ends up being actually very important in the task of dealing with 2 images, because independently, you might have different beliefs about where the chair is, but you might have kind of the same idea of the shape. And so this representational benefit lets you plug this into lots of different tasks and lets you do reasoning over the objects. And this, I think, is very exciting. And so what we can do is we can return to this problem of, okay, we have 2 images. So we can start using this factored representation, and we can start using this to reason about 2 images. And so what we're going to do is we can take this image and we can essentially produce this representation where you have voxels and they're transformed into the scene. And if you run this on an image, you get a set of per object voxels and per object transformations per camera. So essentially, given you're at camera B, you can say, okay, here is where the voxel should be. And this is just a transformation. It's a rigid body transformation plus a scaling. And so actually, this gets you pretty far to the task of trying to put these scenes together. Because what you have to do then is you have to be able to figure out the between camera transformation. So you need to be able to figure out that these 2 cameras A and B, are facing each other. And so what we're going to do is we're going to build on this idea of this factored representation. And I'm going to show you how putting the factored representation together can let you solve and reason about the 2 views very, very nicely. So we need to be able to produce the voxels per object, the transformations for the objects, and the relative camera location. And so you can imagine that we pick one of the cameras arbitrarily as the origin. And so we're going to have to figure out where do the objects go. And you can see that all these transformations have to be linked together. Okay. So the object branch that we're going to use, so we're going to have a branch that predicts objects and deals with them. And so it's going to be built on a paper called 3D RelNet from Nilesh Kulkarni, who was at CMU, and now he's one of my students at Michigan. And it produces the same sorts of representation that you saw before. So it takes an ROI pooling, and it produces voxels, and it produces a translation, rotation, and a scaling. Now, one of the things that's kind of important is it also produces some sort of, you can think of it as a key or a query. It produces some sort of embedding vector that tells you something about the object. It tells you about the identity. And this embedding vector will help us match between the scenes. And so you can think of this as just like a descriptor for the object. And so here we have these 2 images. And so here we have the chair in cyan at the top, the chair in green in the bottom, and the couch in purple. And what you can do is just like, in all the sort of work on trying to learn affinities, you can imagine you estimate the affinities between objects as a dot product. And you can say, okay, the chair in cyan in the top and the chair in green in the bottom, they should have a high affinity. but the chair and the couch, they should have a low affinity. And so you try to, the idea is that you're going to learn how to predict these embeddings for the objects such that when you take the dot product, you produce a matrix which sort of matches the actual ground truth affinity. And so here, of course, like in the previous thing, we're going to need some amount of supervision. So you need to know which objects go with which objects. And so this is, of course, a limitation, but hopefully there are ways to overcome this. Okay. So the way that we do this is you can do this in lots of different ways. In practice, we found that we actually did pretty well if we did we actually predicted this as an L2 loss, where essentially for all the positive pairs, you try to make sure that the ground truth affinity is as close as possible, and the negative pairs are also as close as possible. And there are, of course, different ways to do this, but in practice, we found this this L2 approach to be quite stable to train. Well, what you do is you train the system to predict the objects, their location, their voxels, as well as some embedding, and you sort of train this in a Siamese network, and you can train the embeddings so that essentially they match. And so this produces essentially for every single image, you can run this through a network and get a set of outputs which will tell you the objects and some sort of key which you can use to look up in the other image. So this is partly the way there. The second thing that we're going to need is we're going to need to know how the cameras are related to each other. And in practice, what we found is that we needed a second branch that helped us with this, which handled the cameras. And so you can train a network and you have shared weights between the branches. And you can take their FC outputs and you can concatenate them. And then what you can do is you can train them to predict translations and rotations. And here we just spin the world into different buckets of translation, different buckets of rotation. And this is very similar to a paper from N et al. Called RPNet. And you can basically train the system to try to recognize the relative translation and the relative rotation between these pairs. And one of the things that the deep learning system can do is it can even if you have limited overlap, it can make educated guesses, and it's able to do stuff like taking advantage of the texture. But of course, you can imagine there are different ways to do this as well. We just happen to find that this branch prediction system worked quite well. And one of the key things is that we did this as classification. And this gives multiple outputs. And so you can train this with, this is just regression by classification. And what this does is it enables us to deal with the fact that we might not be sure about some of the relative camera positions. So guessing the rotation indoors is actually pretty easy. You or I can do it quite nicely. Getting the translation right is a little trickier because it's not obvious, because you can imagine for many pairs of cameras, you might be pretty sure that they're within 1 meter away or 2 meters away, but you're not positive which one it is. And so if you do it as classification, you can express your uncertainty pretty nicely. So this produces a set of outputs that you can produce from these two networks. And for every single object, you have the voxels and you have the relationship to the camera that they're seen in. And then between the images, you have hypotheses about where the cameras are with respect to each other. Plus, you have the affinities between the objects in the scene. And so this produces a sort of final set of output, and our goal is to put these all together. So any questions let me know. Just feel free to interrupt at any time for the panelists in case you have questions.
I have a quick question about the affinities. So the ground truth affinities are binary, right?
Yeah, they're binary.
0, 1. And you're computing the affinities by using a dot product, which is between 1 and -1.
Yeah, there's a nonlinearity in the middle that helps sort of.
Oh, I see.
Yeah.
And I assume that you tried metric learning like contrastive loss, because it's a bit weird that.
We tried contrastive loss. It's one of these things where I suspect that if we went back and played with a different metric loss, the one we tried, I believe we tried a standard binary one as opposed to a triplet one. In practice, we found that the L2 one converged pretty reasonably. But this is just an option. If I went back, I would probably try to change it to like just using a standard triplet loss.
Okay, yeah, sure, yeah, thanks.
There's a couple quick questions from YouTube as well. So one is whether the results on NYU were trained on NYU or if they're just transferred from SunCG.
Yeah, it's transferred straight from SunCG. There's unfortunately one of the limitations, and I'll cover this at the very end. One of the limitations of the current systems is we can't train them on raw scans yet. I'm really looking forward to, over the next few years, this becoming a thing we can do. But right now, it's training these systems on raw scans is just, it's very hard.
Because you need volumes or what?
Yeah, you need volumes. And it seems that the combination of scenes, real data, and limited data, sort of you only with RGBD scans, you only get sort of partial surfaces. This seems to be a real challenge. And there's lots of people working on this. So I'm confident there are solutions, and there are lots of really smart people working on this right now. We weren't working on it, so we didn't want to face multiple challenges at the same time.
Okay. One other question is about the voxel resolution and the scale of the scene, whether there's any assumptions about that the scenes would have a certain scale, and whether the images are likely to have a similar scale in terms of like their kind of average distance to objects.
Yeah. The voxel resolution. So one of the advantages of the factored representation is, I think what it enabled us to do is you can get away with voxels for a little longer. So at scenes, it's very hard to get a reasonable voxel resolution. Objects, you can represent, if essentially you assume that most objects are approximately person sized. So they're human-made objects. They're approximately person-sized. There's a certain fixed voxel resolution does an okay job. Of course, the resolution issue is very much one of the reasons why switching away from voxels is I think important. And I'm really glad that there are other representations out there. And I revisited this, I would definitely switch to something else. As for the image size, if you have more stuff in a scene, you can imagine that if you spot a chair that's very far away, you can make a reasonable guess about its shape. Or if it's very up close, maybe you have lots of information to make a good guess. So there is this, obviously the system is not going to work on really small objects, but there aren't any, I think, apart from just the object should be pretty easy to see. There aren't any real assumptions, I think, baked in, apart from the object should be easy to see, and they should all be approximately the same order of magnitude would be my guess. And
just you always have your assumptions built into the data set as well, right?
Exactly. And so certainly like with the data set, it will transferring this to other sorts of problems that won't necessarily work well.
Thanks.
Great. So we have these outputs and you have these voxels, you have these transformations between the cameras and between the cameras and the objects. And so we have to stick these all together. And so one thing we can do is we can just sort of ignore any sort of reasoning and we can just sort of pick the best options. And so what ends up happening is you can sort of pick the top one camera and you can make a prediction. And if you sort of pick the top camera and you sort of merge couches together and you sort of merge everything nicely together, what ends up happening is that the most likely camera, the translation is a little off. So the couches end up being merged together between the scenes, but then the side table gets sort of stuck in the couch. And what's happened is essentially the couches are all in the different locations, they sort of all get merged together. And so what ends up happening is he's predicting the relative location, actually in terms of translation, is quite difficult for a network. And so what we end up doing is we end up trying to reason about stuff. You can imagine you could do the same thing with like the affinities. And so if you take the top matching affinities, it's very hard to actually threshold these. And it might be that there are different metric learning systems we could use which produce better thresholds. But often what happens is we find that there's not really a great threshold that puts them across the entire data set, which puts the right objects together at sort of, doesn't put the wrong objects together. And so you can imagine that you have this affinity thing, which is sort of evidence about which objects should go together. You have evidence about which cameras are possible. And so you want to be able to stitch them all together. And if we return to this image from the Fairmont, the way that we solve it is to some extent we say, okay, maybe you don't start off with a hypothesis about where the camera precisely is, but you can say, okay, well, once I see the bed acts as a way of providing an anchor for where the cameras could go. And so you can imagine that once you get the bed, you can then reason about other objects and you say, okay, the beds fit together. In the same way, you can reason about the cameras by saying, okay, if the cameras are in the right location, then the beds should fit together. And so what we do is you can use like something like the chamfer distance, or basically how well the objects fit together. So left is 0, middle is small, right is large. And we can reason over all the possibilities to try to produce a single interpretation. And so what we're going to do is there's one equation. We're going to do is we're going to have a minimization over a bunch of variables, which tries to put everything all together. And what we're going to do is we're going to select between a set of discrete cameras. And so this is going to be the Cartesian product of our translations and rotations. And then we're going to select a sort of correspondence between the scenes. And this is something where you can drop a part of the scene if it's not matched. So it's not a permutation, but it's a permutation and selection matrix. So think of it as it's at most the sum of the row or the column is 1, and many of them are going to be 0. And the idea is, and this is just sort of giving you the sketch, the idea is that when you merge the scene together, you pick which objects go together and what the relationship between the cameras are, when you put the scenes together, the chamfer distance should be small. Basically, the scene should fit together. And so we want to use just this, but in practice, we found we needed more constraints. And specifically, we need to make sure that the camera-to-camera transformation is likely, that the affinity is likely when we select it, and the number of unmatched objects is, we want to prefer that you match objects. So you don't want to have lots of objects sort of floating around. And so together, these terms enable you to reason about, basically, you want to get the scene to fit together, the cameras to be likely, the affinities to be likely, and you want to match as much stuff as possible. And there are trade-off terms, and we fit this on the validation set, as you should. Okay, so you can reason about this. The question, yeah, or unmute.
Okay, you got it. So this is discrete kind of search you mentioned on the camera transformations and correspondences. So it's not a continuous optimization. It doesn't include any like gradient descent to fine tune perhaps all this. So
yeah, so the search approach is right now we use a heuristic type approach. So the search is, I think, not great. We are actively working on fixing this. And making a much better thing, which combines, which also does continuous search, because you can imagine continuous would make things a lot better, and it does. Although I won't be able to go into it. But yeah, it's a discrete optimization, so you have to use heuristics. But we're working. We know that this is it's a nasty optimization problem, and our solution is not perfect. But it works quite well, surprisingly. With if you have a small number of objects, the optimization is not bad.
Okay, thanks. Yeah.
So what we actually end up doing is we generate multiple possible results. And what you do is once you generate these results, it's very much like Ransack, you basically make guesses about correspondence and the cameras, and you can then rank them according to the likeliness of sort of how well do the scenes fit together. And so you have a heuristic optimization. And in practice on this data set, it works quite well. And we didn't end up running into limitations, and it might be because the number of objects we're dealing with is relatively small. So it's the chairs, the couches, the tables. Now, if you start modeling the chess pieces and the picture frames and the books, well, then you're going to run into issues. But for these objects, it works quite well. Okay, so the data set we're going to use is SunCG, and it's rendered with a physically based renderer from Zhang et al. And so I'm going to jump to the results. Okay. So here, this is the ground truth. So this is the ground truth. And so you can see that you have the two cameras in the scene. And you have a cyan one and a purple one. And you can see that the scene sort of captures, there's some overlap, but not a ton. And a lot of the objects are only seen in one camera. And so let me then show you this is our prediction. And so you can see that we get the general structure of the scene quite nicely, and that the camera's in roughly the right location. So here it is from another view from above. And here it is from, here's our prediction as well. And the different colors indicate whether we had to merge things or not. So red stuff is seen in only one view, blue stuff in only one view, and this green yellow is seen in both views. So let me show you some more results. So here we have a bunch of different outputs, and these are selected, and so this is still a very hard problem, but this sort of shows some of the ability of our system. And so in the left is image 1, middle is image 2. Ours is the third, and the ground truth is the fourth. But here, let's see, it runs again. And this might be a little delayed over Zoom. But you can see that it does a good job of the general structure and gets many of the objects correct. Now, of course, there are objects we don't get, but those are objects we don't model. And yeah, see Derek, unmute.
So, in this setup, the cameras, their position is not known, right? So you're jointly solving over the cameras and the objects.
Yeah.
Okay, cool.
Yeah, and so in some sense, you're reasoning about both, you get better performance in both, which is exciting. So here are some more results. And so here you can see it gets a general structure, and it also recovers these cameras, which is quite nice. Okay, so we have some quantitative numbers, and our questions are basically how well does it work compared to simpler stuff, and how well does it sort of solve some of these individual problems. Okay. So I'm going to talk about sort of how does it work compared to simpler stuff? Because you can say, well, okay, you did this complicated optimization. There's this discrete optimization. Did you need to do that? And so what we did is we treat the problem as 3D object detection. And we're going to compare with the best of a number of basically baselines. We take the maximum over some baselines. Basically, you take the top camera or you take the top correspondence and that sort of stuff. And so we're reporting the best that you can do in each individual category. And we're going to evaluate this as AP. So you try to detect the objects. And we try to get the translation, the rotation, and the scale correct. And so if you get all three correct, then you're, plus I believe the voxels, you get, that counts as a true positive. If you have a duplicate object, then that's, there's a false positive. It's just like standard object detection. And what this lets you do is it lets you sort of tune which criteria you have, lets you understand which parts work and which parts don't work so well. So in 3D average precision, overall, compared to something very feed-forward, the performance gain is actually quite small. So we were a little disheartened when we saw this. We said, oh, 2.1%, oh gosh. But if you actually look at the translation, we get the translations a lot more frequently. And so the translation, if you require it to be only to get the translation right, our numbers go substantially higher. And this is because the translation is actually quite difficult. So this is well known, and people who've been doing multi-view geometry would tell you this, that you can't, this involves the scale. And so you can't necessarily recover this geometrically. So here we're leveraging the sizes of known objects. And so of course, if we take this to a dollhouse, our predictions are going to be wrong. So the translation is harder and requires reasoning over lots of different things. The rotation, it turns out, is actually, it's slightly better, but I wouldn't make too much of this. And this is because I suspect that rotations in indoor scenes, there's this very strong geometric prior, which is that they tend to be Manhattan world. And if you look at the scale is even smaller. And this is largely because I suspect that the data set doesn't have very big scale variation. So in some sense, what we're able to do is we're able to get the translation quite a bit better. But at the same time, overall, for all the objects, the rotation and scale is, there doesn't seem to be a ton of value in reasoning for that. However, what we did is we looked at the performance according to this, how well we reconstructed the single view 3D. So if you take the top 25%, 50%, 75%, and all of it, and you look at the total evaluation, what ends up happening is that if you're able to get reasonable reconstructions in 3D, your performance goes up by quite a bit. In terms of the total average precision, it goes up a ton. So now it's more like 5%, 5.5 or whatever, or 5.7. And if you look at the top half, the number goes a little bit down. And then as you sort of add 75%, and you look at all the scenes, the gap is quite a bit smaller. But what this shows is that the limiting factor for our method right now is our ability to reconstruct each scene individually. And so in some sense, the system, any performance gains on the single view case will translate into performance gains in the 2-view case, which is quite exciting. So these are sort of our initial results. But as you can see, there's lots and lots of room for improvement. So it would be wonderful for people to come in and produce some new method that really beats us. And that'd be wonderful. And there's lots of room for growth in this area. In terms of, we can then ask the question, like, how does it solve the problem? Like, what does it do well? What does it do poorly? And so we started looking at the individual problems. And so we can look at the individual components, and one might be correspondence. And you can ask the question, are these the same object? Now, in seminars, of course, there's always like a trick question, like if the chairs look like they're the same object, you don't know whether, yeah, they are, and there's, they are the same object, or this is just a trick question and they aren't actually the same object. Here you can see they're slightly different, but if you as a human, having been to many vision seminars, are not sure, it's kind of a challenging problem. But if you zoom out from the individual objects, you can see that the chairs are in fact different chairs. And you can say, okay, SunCG, they use the same ShapeNet model. So it's the same chair. This is sort of artificially hard. But if you go to IKEA and you buy chairs for your dining room table, you don't buy 4 random chairs, you buy 4 in a set. And you hope that all your furniture matches in your house. And so it turns out to be even, in the real world, it's still hard without global context to figure out whether the object is the same instance or not. And so, this TV is the same, this couch is the same, this sort of TV stand is the same, but these chairs are not the same. And so what we did is we said, okay, well, before you even analyze how well we perform, we can look at sort of what does the affinity learn? And we sort of looked at, does it learn categories, 3D models, instances? And so we evaluated against metrics which have sort of like a known chance. So AUROC chance is 0.5. So it turns out that you can actually, looking at the affinity, you can predict whether things have the same category or not with like 0.92 AUROC, which is very, very high. If you look at, for example, given that it's the same category, is it the same model? You can still do it actually quite well. So it's able to recognize different types of, it's not just recognizing chair, not chair. It's looking actually at the model. And there's some evidence that it's also looking at stuff beyond just, is it the same instance? Or is it the same model, like 3D model? Because what you can do is you can predict the instance better than sort of just knowing the model. And so there's some sort of signal that we're able to pick up on. And this is presumably just looking a little bit at the context. But if you look at sort of the evaluation, and we can sort of compare with just taking the top one from the sort of affinity that we learn, the top, we're able to sort of improve things by about 10% compared to just looking at the top affinity. And this suggests that what you're able to do is you're able to do things like, for example, these 2 chairs, they look very, very similar. And in fact, you can imagine in other scenes, this type of view, they might be the same. But what we're able to do is we're able to recognize by reconstructing the scene that they aren't in fact the same chair. And we're able to produce signal via that. So we're able to do that. We also looked at the relative camera pose, and we sort of looked at how accurately you could predict this. And so for translation, we're able to do much, much better. And this is because what we're doing is we're leveraging the fact that we know the sizes of objects and how far away they are from each other. So, you're able to get a much better sense of, these 2 cameras are say 1 meter away versus 5 meters away. On the other hand, our performance on rotation is quite a bit worse. Or sorry, it's not quite a bit worse. It's there's not a huge performance gain. And so compared to translation, we don't make as much of an improvement. But if you've looked at a lot of indoor scenes in your life, and I've spent a lot of time looking at pictures of indoor scenes, you know that indoors there's a lot of texture gradient that tells you the rotation of the camera with respect to the scene. And so what this, even before you do any reasoning, you can do very well on rotation simply by looking for this. So I've shown you some successes, and I want to show you some failure modes as well. So sometimes, the pairs that we get are very hard. So this one, I don't even know what I would do here. And so certainly there are failure modes like this, which are kind of, if the reconstructions are bad, the scenes are challenging, it's not going to work. And so there's certainly results, I showed you a lot of nice results, but there's plenty of room for growth in this area. But there are other failure modes that that sort of got asked about earlier as well, which is when you have this optimization involving discrete choices, handling lots of different possible correspondences is really hard. And so if you enter this restaurant and you try to get our system to find the matches between all the chairs in the restaurant, it's going to have a bit of issues because this is a very, very hard optimization problem. And so we certainly can't handle tons of objects right now. And so this is a limitation, certainly. And there's also, here actually the ground truth, if you look at this overhead, there are actually 3 beds. And our system produces sort of 2 beds. And so certainly there are cases where the single pair of images is not actually enough. So this is actually a very reasonable inference for our system to say these 2 beds match. As it happens, it's like there isn't evidence for a 3rd bed, and our system produces these results. And so in some sense, there are certainly 2 views is, it's an interesting case, but it certainly doesn't fully constrain the 3D scene. And so one thing that we are looking, what we're looking at is, can you handle lots of different views? Like, what if I give you 3 views? What if I give you any views starting from 1 and going up to say, 10? How can you reason about stuff jointly? And so these are some of the failure modes, and some of them are more boring, just like the 3D system doesn't work. Some of them point to limitations of the data, and some of them point to limitations of the method. I always want to show a little bit of natural data, which is basically just to show that the system, we train it on SunCG, it doesn't completely fail on natural data. So here's a result from NYU V2. And it's a little sparse because essentially we reconstruct a set of 6 objects. So we get the bed in blue on the right, we have the chair in yellow, and we have 2 TVs in red and orange. And you can see that it doesn't get the full layout of the scene. There's not the walls and the floors. There's lots of stuff like books. There's stuff on this person's bed. There's lots of things that we're missing. But what you can see is that the system doesn't produce total junk when it's applied to natural data. And part of this is, deep nets appear to generalize pretty well. Part of this is that the people who rendered the data knew what they were doing and rendered it well, so it would generalize well to NYU too. But this is a nice test to see whether the system actually produces any reasonable results. So I'll conclude with some limitations. So I've shown you some stuff and I've shown you a bunch of successes, but I'll talk a little bit about the limitations of the problem. So first, synthetic data is certainly a very limiting factor. Right now, we depend on synthetic data to get ground truth. It currently reconstructs sort of 6 objects, and the optimization and the architectures are a little bit sort of squirrely. So we have to have separate branches for the camera, separate branches for the objects. And the optimization, it's a hard problem because it's discrete optimization. And as was pointed out, it doesn't do continuous optimization. So these are some of the limitations, and I guess we have a bunch of time. So I can take any questions if there are ones on the YouTube before I show some overcoming of these limitations.
Yes, thank you, David. We have some questions. This is from Alberto Tono. When you identify objects, say a chair, how much subclasses do you think you can handle? Different kinds of chairs, wheelchairs or office chairs, those kinds.
Yeah, so we don't specifically know that they're a chair. So any results where we look at the chairs, it's simply this is just a post hoc analysis where our system doesn't assume that we know the names of the objects.
Yeah, or if you think you add labels, how much do you think you can do?
That's actually very interesting because that would I think this is a fascinating question because obviously people name there's a reason why things are called chairs, and this tells you something about their form and their shape. So you might be able to sort of improve things by that.
It could be another big field actually. Other people working on. Yes.
Yeah.
Thank
Exactly.
you. Vangelis, you were about to ask a question.
I do have a small number of sort of dessert slides to show you some.
Okay. Yes. Maybe I'll let you go for the dessert slide first.
Okay.
Other questions.
Okay. So there are these limitations, and as you can see, if you go back to here, working on natural data is really hard. And volumetric, there's a lot of great work on trying to reconstruct volumetric things from single view images and learning it from natural data. But we wanted to sort of, some of the stuff that we're working on right now is to try to overcome this, even if we can't reconstruct things volumetrically. So I want to show you, so here are results from the Matterport 3D data set running in the habitat simulator. And so this is a step up in terms of reality. You can still, I know graphics people look at it and say, I can see immediately. You can see sort of issues, but it's much more natural, and it's quite nice, and it's a real rendering. It's a rendering of a real space, and so we're building systems right now, and this is a work in progress, where we can sort of do the same problem, and we're trying to do this with planes. And there's been a lot of work on planes, and you can imagine you can sort of reconstruct these natural scenes using planes. And so you can't handle volumetric stuff because it's very hard to learn this on real 3D scans because they're not watertight, they have holes, they have noise. But planes we know how to do it. And there's been a lot of great work, including from Yasu, on trying to reconstruct planes from images. And so here's from one view, here's from another view. And so you can see, you can sort of take these 2 views and stick them together. You also don't know the camera. I'll show you another one. So here we have sort of Matterport is always interesting because it's scans of places of people who can pay Matterport to take the scan. And so you always get these very interesting houses and locations. And so you can see it gets this very nice and clean and beautiful bedroom, and it's able to reconstruct it. And you can see certainly the planes are not perfectly aligned. This is certainly not at the level that you can get from having lots and lots of cameras and sort of reconstructing things. But here we're handling two cameras and we don't know their relationship. And finally, you can sort of see here is like a garage. And so here we're able to do a reasonable result as well. And of course, whenever I show good results, I really want to always show that there are sort of failures. And so here, certainly this is a work in progress and there's tons of room to go. And so here, we try to reconstruct stuff together and we get this sort of junk mesh of just stuff being put together. The planes are at different angles. There's still lots and lots of room to improve in sort of 3D from a very small number of images. So that's sort of where this is heading. But I want to talk a little bit about looking towards the future and where I'm hoping 3D is going. It turns out this sort of multi-view, this sort of having two images that you don't know the relationship is something I worked on like 10 years ago. And this is sort of what passed for results 10 years ago. And so here we were really excited to be able to match planes between two images fairly reliably with multiple planes. And I was we were very excited. This is very cool. And right now we're able to produce sort of from a single pair of cameras with an unknown relationship, we can actually do an okay job at reconstructing the scene. And I think 3D has made amazing progress in like the past 10 years, thanks to really an amazing community. And I really want to thank the organizers for running this. And there's been a lot of wonderful discussions, and 3D is such a broad field that we've been able to have these great discussions and learn from different parts of 3D. And I think what I'm excited about for the future is that I think we can be useful in sort of new settings, thanks to this fusion of learning and geometry. Because there's lots of lessons we can learn from the classic approaches, because 3D reconstruction, it's a real problem. There's a real physical understanding. And so there's two things I'm excited about. And one is sort of figuring out what outputs do we need for roboticists to need to use our 3D. So roboticists, I always want to get roboticists, hey, do you want to use my system? And I'm looking forward to, in the next 10 years, having roboticists say, yes, I want to use your system. I will not have a system which doesn't take advantage of learning. And then how can you reliably 3Dify everything? And so I think there are lots of areas where we can sort of apply this learning and geometry together. And last, I think there are lots of other areas. For example, I'm currently working with bird biologists to understand climate change and how birds' morphology changes. There are lots of people who could actually use 3D as a service. And there are lots of new problems that now we can actually tackle and make progress and help other fields have a positive impact on the world. And so there are lots of problems like this where you can actually really have a nice impact by providing the technology we have in computer vision. Okay. So closing thoughts, and then I'll shut up and take questions, is that reconstructing this wide and unknown baseline is a very interesting task. And I think there's lots of ideas for room and growth. And I think the last decade of 3D was really great. And I think the next one will be even better. We're really set up for doing a lot of interesting problems that we really couldn't have dreamed of sort of 10 years ago. And so thank you all. I'll take any of the questions that I know there are.
Thank you very much, David, for the great question. And also thank you very much to Vangelis, Derek, and audience already for many great questions. We still have two audience questions. Let me shoot them first, then ask the panelists to join later. So the first question is from Fouhey for your volumetric representation. Use binary volumetric. The other is more algebraic, neural radiance field style, meaning you put X, Y, Z, you get value out. Do you see any difference? Is it more about the precise surface smooth, which you don't really care about? You more argue distance, rough shape. Do you see any difference in these two representations for your task?
Yeah, this is a great question. I think in our particular case, the volumetric reconstruction, I think we can use anything. I think one of the things that I've learned over the past few projects is that there's kind of the shape of the object and there's where it is. And these are somewhat separate. In the same way that reconstructing objects in 3D pose estimation, they're a separate project with separate fields, separate people, separate metrics. And if you're trying to reconstruct in scenes, you have to do both. And I think here, stuff like NERF, you can imagine applying this and producing much better local understandings of objects. And you can imagine using implicit functions, and they're totally separate. I think the value, though, is having a sort of a coordinate frame attached to that object, so that it's not a bunch of voxels or an implicit function floating in space. It's actually like there's like a bounded volume where you're trying to understand the occupancy.
Yeah, thank you. And the second question from the audience. This is from Chu Han Zhou. There was a point, synthetic data is the limiting factor. Is it because the synthetic rendering is not as realistic, or is it synthetic data covers only a small portion of the real 3D scene distributions?
Yeah, I think it's a limiting factor in both. It's a limiting factor in the sense that right now the systems that we have are also kind of really, they're addicted to the really strong supervision that you get with synthetic data. With synthetic data, you say, this is what I want as the output. And it's very easy to say, just produce this output. And so I think it's a limiting factor in very many ways. As it happens, it's enabled us to explore new problems because now we have this strong supervision. You don't have to think about how do I learn how to do this from just a camera, just ordinary pictures off the internet. That's a very hard problem. That's a 20-year problem. So it's a limiting factor. It's enabled us to go farther, but in terms of actually deploying it, it does end up being this limiting factor. And there are definitely ways to improve the realism. I think there's fantastic work. We were using one system, but there's been a lot of work by a lot of really smart people about how to improve the realism. And it may be that if you have really good, really realistic synthetic data, it will work amazingly on ordinary sort of images that are not synthetic.
Yeah, thanks. So let us now move on to the panelists' questions. Maybe Vangelis, do you have questions to ask?
Yeah, well, I already had some questions during the talk. First of all, thank you, David, for the great talk. Let me also turn on my camera. So the embeddings that you get are supposed to be view invariant representations of objects, right? So that two instances are matching under different views, right? Are they capturing also color textures? So are they the same under different colors and textures of objects? Did you do any analysis on this, or there was some confusion if similar objects with same geometry but different textures, would they have high affinity?
That's a really great question, because I think so. When we originally worked on this problem, we made this affinity matrix, and we get the results, and we sort of put the results on the table. You're like, numbers are high, great. And then we said, well, what is it actually learning? Because it should be, in some sense, is it actually the geometry? And we thought first, oh, maybe it's just recognizing the category. And what we've learned is secret chair detector, and we were a little worried about that, but it seems to be it's able to learn models as well, and it does instances a little bit too. And it's certainly not just it's recognizing the 3D model. The question is, like, with texture and color is really interesting because it also gets to, Derek had this point about, well, there's also the data set. And there's this tension in a lot of these works of, in geometry, you could imagine that certain chairs could have certain colors. You could have a chair that is like, I don't know, it has some very weird color. It's you can actually imagine that certain chairs are likely to be gray and certain chairs are likely to be brown based on the shape. And there's this relationship between the two. But that's not really a real physical relationship. And if I painted a metal stool, a very weird color, you'd have no issues recognizing it. And I suspect that the network is secretly leveraging a lot of information about the color, and it's not quite the geometry. But this is I think a fascinating question. And there are definitely people who, as Yasi said about the question with language and objects, there are definitely people who study this. And I'd be very curious to see if, for example, humans take longer to recognize or verify the geometry of an object if the color appears very, very different, or the texture appears very different.
Great, thanks. Another question is, how would you extend this to, any thoughts about extending this to multiple views so you would have pairwise affinities between all pairs of views? Like, how would it scale, more or less?
Yeah, the current system is going to have some issues. We played around with it a little bit, but not a ton. You end up having, there is, of course, the fact that, as Marshall told me, I still can't wrap my head around it, but with the trifocal tensor, you get more information from 3 images than individually from the 2 images. And so there might, I wonder if there are systems where you have to solve it, whether you can solve it all independently with 2, or whether you actually have to, there are special relationships you actually have to solve when you have 3. It certainly, if we could get the optimization to be faster, I suspect we can handle lots of images pretty reasonably well. The catch is that you have to sort of propagate this information through all the images, and I can imagine this would be a very difficult problem. But the representation, I think, would enable you to do it. I think there's a question of the optimization and whether that can happen.
Right, I see. Yeah, I could imagine that you could have like more constraints when you have multiple views, like you want the pairwise camera transformation from scene A to B and then from B to C, and then you have C to A, you want maybe to form some kind of cycle consistency. I'm just thinking out loudly here.
Yeah.
Some more interesting like relations coming up.
And then you get these, you presumably also would have like sort of loop closure things. And the thing with the optimization is with, loop closure is this very, very powerful constraint. But it also requires, you have to figure out, you have to optimize everything. And then there's this, it's not that you're slightly adjusting the cameras. As you chain this stuff together, all of a sudden you really have to move lots of things. And I suspect the optimization would be tricky, although there are certainly, there are lots of people working on this. And I can imagine that if you plug and play, and there's work, of course, by the way, with semantic SLAM and other efforts, which use some of these constraints, although it's more like you have a continuous set of views as opposed to, for example, one view every 10 meters in this sort of disorganized bag.
Great. Yeah, I don't want to monotonize the discussion, so let's proceed to Derek, I guess.
Sure. So first, I guess I want to compliment you on your choice of problem. I think that I agree with you that I think this like 2-view or few view or mixed view or whatever is like a really interesting area where there's like a lot more to do than there is in either single view or multi-view. One thing I was thinking about and noticing is that you can either come at this kind of like few view problem from a multi-view perspective, where you start with like structure from motion and stereo, and you say that you have like an incomplete representation of the scene, and then you want to complete that based on recognition or imposing structure or something else. Or you can take a like object recognition person's perspective and say that you're going to start by recognizing stuff in each image and then try to make it consistent. And you obviously chose like the more recognition approach, and that kind of leads to the discrete optimization and all the flavor like is in the single view flavor. So I was wondering, what do you think? And I think part of it is because when you only have 2 views and they're very lightly interacting, then the multi-view part is relatively weak compared to single view. So one thing is like, have you thought about it, like if you add more views or even from this 2-view case, and if you were to take the other tact, like how would you approach it? Have you thought about approaching it from the multi-view side? Or is there like a more balanced way of doing it that where neither one is dominant?
Yeah, because there is this flavor. It's kind of like you get your stuff and you stick it together, and that is, it's certainly it was certainly inspired by the fact that you really don't have this. The 2 views very lightly interact. I wish I knew what the answer was for something where it wasn't one or the other is dominating. I feel as if you could imagine that in some sense you might want to actually, without making the method complicated, you might want to have some sort of approach where you iterate between the 2 views in the sense of there are 2 views of the problem. Because in some sense, it's more, you're right that this is you're finding the cameras as almost like a byproduct of the optimization as opposed to a sort of first thing. And one of the things that we're not dealing with right now, we're using objects as these ways of finding correspondence, but we're not taking full advantage of the fact that there's lots of other work. There's great work on like wide baseline stereo, because this is obviously, the cameras themselves are a very recovering the cameras themselves is actually a very useful output, and so there are people working on this. I'm very curious to the extent to which we can handle these some of these cases, and so we have some results that suggest that when the views are reasonable, these wide baseline approaches can actually work quite well, and you can imagine they initialize things quite well. And sometimes it just completely fail. And I think that there's this bigger question of how do you have these components? How do you make a problem or solve a problem where, in some sense, sometimes the components can completely fail? Like, for example, if you're trying to register, if you have basically no overlap, you can imagine even with learning using the shape of the scenes, you can make reasonable guesses and you can say, okay, hey, how these fit together. But right now I don't have I think the reason why we took the single view case is that the multi-view case, it can have these sort of catastrophic failures. And then you're sort of left with you're in the, you tried, and now you're sort of in the catch setting of the problem. And I don't know what you do there.
Mm-hmm.
But
yeah, I think it may also depend on your type of images. Like if you had two 360 images, then the success rate of multi-view will be much higher because obviously you have a lot more overlap in that case.
Yeah.
Where in this case, this is like the images that you're showing are extremely hard for like interest point ransack or something.
Yeah. And you can imagine that there's also this there's this interesting tension as well with sort of the problem selection as well. With do you pick sort of the problem which you would have to be able to solve? Like, humans can do this pretty well, but you can imagine that actually you make the problem slightly easier in a way which is very realistic, in the sense that nowadays cameras or phones come with tons of cameras. There's all this extra stuff, all this extra information. And so I think there isn't a really great answer for which problem you should tackle, but I think what's exciting is that there are lots of people working in this area. There are people, once you have the cameras, then obviously you can start reasoning about a coherent volumetric 3D space. Like you can have X, Y, Z, and you can reproject it. And that's a very powerful constraint that we're not using right now. We're sort of using it indirectly, but we're not really using it that well. And so I think what will be interesting is, over the next 5 years, what sort of paradigm ends up being the one that people pick.
One other question I have is, if you could have any data set, what would it be? Like if somebody else is going to create it? Because these 3D data sets are pretty hard to make. So I think most people would say they don't want to do it themselves. But if you could magically create it, what would it be?
Yeah, I love this question, because I feel as if when I started, and when many students start out, they're like, oh yeah, I just collect the data set, it's fine. And occasionally I show this picture of, there's this picture from actually your paper with Natan Silverman. And there's a picture of him holding a Steadicam. I always show, when I talk about data in my class, and I say, okay, yes, you say, yes, I'm going to collect a data set. But this guy, he spent a year, and we got 1,449 really great images. And this data set was fantastic, but it took a year. And it's like, or certainly a very long time. And so it's very hard to collect. And it's, I think data set creation is not, I think the community doesn't reward it well. And I think it's a pain. But
I don't know. I think you get rewards, but it's hard when people are used to collecting their data from Flickr. You get a false sense of complacency. Yeah. And then when you do 3D, you're like, oh my goodness, I actually have to go into every single scene and then do all this processing and stuff. Yeah. But so what would it be?
I think it would probably be really big in terms of sort of the locations. I think sort of ordinary locations would be probably the most interesting but most difficult, because once you start collecting data, there are all these considerations you have to take into account. There are all sorts of privacy issues. There's the fact that once you collect the data, I remember Natan telling me about this, where he'd say, oh, I'm going to go over I'm going to go over to your house. I'm going to collect data. They sign the thing and say, wait a second, hold on. I have to clean my house. Like, well, but then you look at the Matterport images, and they're perfect. They're beautiful. They're like, my parents would be so proud if I lived in this clean of a house, and they'd be like, oh, you make your bed.
Because nobody lives in those houses. They're just staged, right? Usually.
Yeah. And I think if you could get this realistic in setting, that would be very exciting. I think one of the big problems is I think that right now 3D, like sort of 3D sensor type stuff, there hasn't been like a killer app in terms of, for example, robotics, that would get someone to say, hey, I would like to have a robot, and I understand that if I have a robot, occasionally there might be pictures that people use. If people could make an informed trade-off about that. But you'd like to have sort of real, actual pictures, because you talk to roboticists, you know this. You talk to them, and they say, we tried your system, and then they show where you tried it. It's this cluttered lab. There's stuff everywhere, and it doesn't work. And it's partially just because I think our data is often very clean. And you look at the images that we have up here. This is wow, this is amazing. It's like a real estate person is trying to show this house. I just wish we could get sort of cluttered real life data. That would be the sort of real, that would be my hope.
Like laser scans though, or meshes, or graphics with texture on it? I mean, like what kind of representation?
I think we should. I think laser scans plus corresponding pictures would be great. I think I would. The part of me says I really want volumetric stuff. I would love to have volumes attached to all these objects because that would make my life very easy. But I hope that 3D sort of is from n images, where n is small. I hope that we can wean ourselves off of supervision a little bit. And I feel as if we had this amazing data set and it had volumetric stuff. The solution would be, yeah, you train a deep network and you have strong supervision for everything. But something like, basically if you could scale up replica, that would be amazing. Like scaled up replica, like everywhere and not so clean.
Scale up what?
Replica data set from Facebook.
Oh.
That would be very cool. What would you like?
So, well, the first thing I would want is just like a lot more multi-view data sets where you have ground truth that are like real data sets. So like ETH, for example, because all the data sets that we do have are either like, they're typically very small and very limited in the types of scenes they have. Then once you had that, then you can turn that into like you can add like object recognition and 3D shape annotations and stuff like that. So I think first, kind of like what you said, is like laser scans with corresponding images of common scenes. And ideally do like different kinds of capture. So like do like a 360 capture as well as perspective capture, so that people because it's the 3D data that's really hard to get. It's easy to take different kinds of images. So that way people working on different kinds of problems can use that data.
So who's going to collect it?
maybe we'll do it. I saw that there's a question in YouTube as well.
Yes, maybe I'll throw in. This is from Vibe Have Meta. This is more higher level, interdisciplinary question, which Derek may also have a comment. He's doing the construction / computer vision. The question is, what would be a real world application of the solution? Like Airbnb style auto labeling amenities, apartment, or robotics, or others? You see certain like our interdisciplinary aspects of the solution.
I think that's a great question. I think, so this was sponsored by Toyota, and they have this very strong emphasis on indoor robotics right now. And they have really great robots. They have really interesting problems. And I think so there is this phenomenon that often when you are coming up with solutions for robotics things, there's kind of this sometimes there's a hidden initialization cost of, you go in, you make this map of the environment, and then once you have the map, everything's fine. But there's, if you want to deploy stuff, you can imagine that systems like this, if they, as they get better, like the systems are not mature enough to stick on a robot. I'm not standing between, I'm not going to have a robot that can exert a large amount of force depend on my system right now, maybe in 10 years. But you want to be able to reconstruct the full 3D and stuff like the volumetric stuff, where the floor is even behind objects. You want to be able to produce sort of these invisible bits of the scene. And you can imagine that having multiple views and being able to reason about them and to reconstruct stuff, this is a useful skill for ability for a robot, so that when it enters a room, it doesn't have to first do a whole bunch of pass around and bump into stuff and or get stuck, or for example, not know that there's a floor behind the bed. It sort of produces an initial map that you can refine with much better stuff from, for example, from LiDAR. But I think the real value, and Chris Atkinson used to give me a really hard time about this at CMEO. He asked, I'll just stick like 10 laser scanners on my robot, or 100 or 1,000. And I think the thing that finally got him to say, okay, maybe I'll have to think about that, was what about invisible parts of the scene? And I think this is where the real current value is, because you can't get that from sort of traditional laser scanning. Although I know that there are people working on trying to see behind corners and through walls and that sort of stuff. But I'm very curious about Derek, because he's got this amazing sort of.
So yeah, so one thing is I'm actually not as sure about the robotic side of things, because I think there's still an open question about whether you want a complete scene representation or like a complete detailed scene representation, or whether you should be just representing your current view in detail and represent the rest of the scene like very coarsely, like a kind of coarse map. But I would definitely agree that you need some kind of interpretation on top of the geometry, so that like a vertical geometry like points is definitely not enough for a robot to do useful reasoning. And then in terms of other practical applications, so one is just like kind of like photo touring. So like the Matterport style, being able to see the dollhouse of the apartment and tour it. So generally like things that have visualization kinds of applications are always safe for research that sort of works, because nobody gets hurt if it doesn't work. And then like at Reconstruct, we use 3D geometry and can use this kind of thing both for actually like the geometry itself is important. Like when people want to know, did the room get constructed to scale? Are the pillars in the right place? Did they put the window in the right place? As well as like once you incorporate recognition, then doing things like progress monitoring to know like how many did they lay all the pipes they were supposed to? Did they put in the ventilation? Did they finish the windows? And also like quality checking on all of that stuff too, to make sure that everything was done according to specs. So there's like I think there's definitely a lot of applications in having geometry and some kind of semantics together, so that you know what and where everything in the scene is. And in construction, people really want that too. People are there's a lot of like the innovation offices and project managers and stuff really want the ability to be able to automatically say, get some ground truth on like what is like the stage of construction in different parts of the scene and how far along are the different crews, because because these projects are quite complicated. So having that would be helpful.
Yeah, thank you, Derek. So maybe it's almost running out of time. So switch to Vangelis for the last question, and we'll wrap up.
Yeah, one last question is that I see lots of work in indoor scenes, but what about the building exteriors? Like if you want to apply such approach to maybe detect, and reconstruct buildings, windows, maybe surroundings of those. What is the limitation? The data set, like synthetic data that doesn't exist there, or scalability as well on getting,
Yeah, this is a really fascinating question. Because it is, I think the reason why everyone does indoors is the data that's available. Like the sort of, I would love to be able to do sort of reconstruct like really huge city scale type stuff, where like, for example, like, the sort of like, you move to a new area, like you walk around, or you sort of reason about stuff, and you have this ability to reason about the bits of the scene that are missing, imagine the rest of it, make reasonable inferences about the backsides of houses, how you would take shortcuts through stuff. And this connects to like lots of, there are people doing work on this in navigation. Of course, with robotics, people have been doing this with more classical methods for a very long time, and also learned methods on top of classical stuff. But taking stuff outdoors would be really exciting. Some of it is the scale. You can imagine like, how could you take, like a picture like when you're landing in a plane, you like fly over New York or something, you say, how could I reconstruct all of this? Or like, how do I understand all of this from this image? And I'd love to know the answer to that, or have a system that could actually reconstruct all of New York from an overhead photo. That would be amazing.
Graphics can help here. I mean,
Yeah.
we have lots of 3D models of buildings, like in 3D warehouse, and like there's procedural modeling of buildings that maybe can generate synthetic data here.
Totally. Sometime when I was at Berkeley, we tried to figure out how to get the sort of overhead views from Google Maps, but then if you attach a debugger, they stop showing you 3D. But yeah, so I mean, graphics certainly help, and I think. But I think the interesting thing as well is like there's this huge scale and there's this common sense and there's like how can you go from like the details, like you look across the bay from Berkeley to San Francisco, you can see everything. And you can imagine like the little tiny details on the windows, and you can imagine that you look at the window, you can say, I know that that's kind of a little bit recessed. And you can say all these things that are just like about things that are so far away and at such big scales. I'd love to be able to have a system that does that handles going from like the tabletop to like a full city. But yeah, I think some of it is also on the sort of the learning side, even if you can get the graphics to render it.
Great. So with that, I'd like to thank David, Vangelis, Derek, and the audience as usual for joining the seminar. Next week, 3DGB will be back to Asia. So thank you very much again, and have a nice day.
Thank you so much for hosting this. It's been a pleasure.
Thanks, David. Thanks,
Thank you.
Yasu.
Bye.
Bye.